So here it is. Here's the big proof that we're going to prove that the set of all infinite binary strings, that's what I've got here, 0, 1 to the n, is uncountable. So here's the proof. Suppose it is countable. It's a proof. This is going to be a proof by contradiction. That is, we're going to assume the exact opposite of the thing we're trying to prove, and we're going to prove that assuming the exact opposite leads to bad results. It leads to a logical paradox. Meaning, if we end up, and by the way, with a logical paradox, is a case in which some proposition P, let's say, is simultaneously true and false at the same time. So it's both true and false. And in mathematics, we assume that we've done things right and up till now, and so we by that have the fact that we don't have any paradoxes. We don't have any paradoxes in math. Essentially, what we're assuming is that ZFC is a consistent set of axioms, and we'll talk about that in a long time, in later. But it's a safe assumption to make. If you need a quick way to believe me on that right now, you can prove that if any paradox exists in any system of axioms, then every single statement imaginable is a paradox. If there's one paradox, then everything is a paradox. So we assume that we don't have paradoxes in math, and so proof by contradiction is a way to prove things because we basically assume that the statement that we're trying to prove is false, and then arrive at something within the proof that is both simultaneously true and false. And then since math has no paradoxes, we have to conclude that our initial assumption that the thing was true can't be true. And so that's kind of what we're going to be doing here. So we're going to assume that this set is countable. And proof by contradiction are very useful because assuming something directly like this usually gives you something that you can work with. And so what do we get that we can work with right now? If we suppose that 0, 1 to the n is countable, then have a bijection. Maybe I should say enumeration of all infinite binary strings. And so I can list them in a table. And so I'm going to draw that out now. So here's my table. I'm going to make this very big and clean. And so here's the list. Basically, this is going to be the first string. This is going to be the second string. This is going to be the third string. This is going to be the fourth string, fifth string, sixth string, seventh string, ... And then this will be the first digit of the first string, and this will be the second digit of the second string, third digit, third string, fourth digit, fourth string, fifth digit, fifth string, sixth digit, sixth string, seventh digit, seventh string, ... I want to list out plenty of strings so that we can see exactly what's going on very clearly, because what's going on is very simple and very stark in what it brings about. So, maybe the first string is 0, 1, 1, 0, 1, 1, 0. Maybe I even need more than this, honestly. Well, I'll leave it at that. ... So that's the first binary string. I have some enumeration, and I'm just kind of like pretending it's this just for illustration. It doesn't need to be this. Maybe the second string is 1, 0, 1, 1, 0, 1, 0, ... and so on. I'm gonna skip to the part where I've drawn all of these. Okay, so I've written out my table here. So this is my list. I've basically just listed all of the infinite strings going down. That's exactly what I get by assuming that the set of all infinite binary strings is countable. And so what I'm going to do now is I'm going to look specifically at this. This is going to be kind of hard. I want to look at the diagonal elements. And since this does go down forever, this goes on forever too. Consider the diagonal string D, which is 0, 0, 0, 0, 1, 0, 1, dot, dot, dot. So this is a string, and it's an infinite binary string. So I've constructed this table, given my enumeration. Again, it doesn't have to be this. I wrote out a particular case, but it doesn't really matter. I'm just drawing this for illustration of what it is that we're doing. We fixed a bijection. We fixed an enumeration. We have one. And we're considering this diagonal string D. So out of this table that I've made, given what I had, I've constructed this binary string D. Actually, what I'm going to do is I'm going to take this diagonal string D, and I'm going to call it D bar. And what it is it's the exact reverse of D. I'm going to actually invert every single bit. So it's going to be 1, 1, 1, 1, 0, 1, 0. All bits reversed. And it goes on like this forever. These are infinite strings, but you get the idea. So this is an infinite binary string. Now, D bar is an infinite binary string. So it must appear somewhere in the table. So essentially, you can kind of think of this as like, this is n, and then this is f of n, where f is the bijection, right? So it's got, there's got to be some n such that this D bar is equal to f of n. There has to be, otherwise f wouldn't be a bijection. Which we were assuming that it is. So it has to appear somewhere in the table, but where is it? Let's think about where it is. Well, where can it be? Like let's just kind of look at the first one. Can it be number 1? I know it's not number 1, but this is just a hypothetical table. It's kind of, these are all kind of I should have done all of these in symbols, but I'm just kind of doing the particulars. So let's just think, can it be number 1? Well, no. Because well, why? Well, because the first element, the first bit of the string of the first string is a 0, and D has its first bit as a 1. But the important thing to note is that it's a 1 because I specifically reversed it. No, because a string starts with a 0. And D bar starts with a 1. Can it be number 2? Again, no. Why? Well, it's because of the second bit. The second bit is a 0. Because, again, string starts with a 0. D bar, not starts, excuse me. Doesn't start with a 0 at all. No, because second bit of second string is a 0, and D bar starts with a is a 1. Not start, I'm sorry. And the second bit of d bar is a 1. Zoning out. And second bit of d bar is a 1. So it can't be. What about the third one? No, it can't be the third one either. Why? Because the third bit of the third string is a 0, and I flipped it. Can it be the 12th string? No, because whatever the 12th digit of the 12th string is, whatever the 12th bit of the 12th string is, d is the reverse of that. Say it's number I for some I. Say it's anything. It's got to be somewhere, so let's just say it's the ith one. Then ith bit of ith string is something, and d bar is the reverse of that. So it can't be. Do you see the paradox? If I assume that d bar is the ith string for some I, then I get immediately that it is also not the ith string. So d bar is the ith string and also not the ith string. Contradiction. And I don't know how common this is. A Chinese friend of mine is the first person I saw to ever use this. But I like to draw this symbol to mean contradiction. But yeah, that's it. So we've constructed an element d that just can't be anywhere in this table. If we assume that this table exists and is comprehensive, then we immediately get out of it, we can construct out of it an element that can't be here. And that contradicts the assumption that this is comprehensive. So what do we have to conclude then? We have to conclude that such an enumeration does not exist. In other words, 0, 1 to the n cannot be counted. Is uncountable. Now, maybe this is complicated to you. Maybe it isn't. I tend to think that a proof like this is pretty simple in considering how big it is as a result. It's a really fundamental fact about mathematics. And the argument here is called the diagonalization argument. This proof method, it is a proof by contradiction, but more specifically, it's called diagonalization. And it's something that we're going to see reoccurring multiple times. In fact, the conclusion from this, which I'll write down in a second, is that not all problems are computable, because there's more uncomputable problems than there are computable problems. There's just it's a fundamentally larger set. But we're going to construct in the next video or two a specific problem that is uncomputable, and we're going to do it in more or less the same manner that we did this. You can prove all sorts of things. A lot of proofs in computability theory are very similar to this proof here. They're all diagonalization arguments. We've diagonalized out of the set. So building d bar, we say that we've diagonalized. Sometimes you hear people say we've diagonalized out of the set. We've kind of proven that two sets are the same by assuming that they are the same and then building our way out and then just kind of breaking out. We've diagonalized out, and we obviously it's kind of clear why we're saying diagonalize, and there's something fundamental going on with the diagonal here. And the original kind of idea for a proof like this is definitely credited towards Cantor. But yeah, that's it. That's the proof. So what's the conclusion to that? What's the fallout? So corollary, the set all, the class of all languages, is uncountable. We've also got that the real numbers is uncountable. Also, recall that the rational numbers are countable. So it's not until you get to the real numbers that you get an uncountable set. And so because of this, the big takeaway is that the vast majority of decision problems are not computable. Now we're going to construct a particular example, several actually, in the coming episodes. But what have we got here really? How do countable sets kind of compare to uncountable sets in terms of size? I mean, what we've essentially said here, I hopefully have convinced you that the inability to count a set means that the set is fundamentally, in some sense, bigger, right? Because you cannot define you can't define a surjective set. You can't map onto it. You can't cover it. There's not enough things. That's essentially what we said. Remember, the original idea is that we have two sets, and in the case of what we just proved, this is the set n, and this is the set 0, 1 to the n. And what we've basically said is that there's just too many points in here. I can define, I certainly can always define an injective function from the natural numbers into here. I can define this guy going here. Go away. I can define this guy going here. I can make an injective function. But not surjective. Not onto. In other words, I can make a one-to-one association with this guy and this guy. I can inject n into here. I can embed it in the set 0, 1 to the n. And indeed, right, the set of all countable, the rational numbers are all real numbers. Q is a subset of R. All rational numbers are real numbers. You don't need to undo the embedding. The embedding is done already. But this is a countable set embedded in an uncountable set. So to compare countable and uncountable, maybe that's what we should do. Maybe we should think about the rationals versus the irrationals. To compare countable with uncountable in terms of size, let's actually think about that for a second. I'm just going to say it out loud. One common thing you hear is if you were to make a dartboard out of the real numbers and throw a dart at the dartboard, the probability that your dart hits a rational number is 0. You will not. That's how much bigger the rational numbers are, that's how much bigger the real numbers as a whole are compared to the rational numbers. The rational numbers, this countable set within the uncountable set R, is insignificant. It's just not even possible practically. It's certainly not going to happen that I hit that. Now, probability 0 does not mean it's impossible. If it happened already, then it happened already. But the probability is 0 means that it's an insignificantly small event in terms of probability. Another way to think about it, if you were to color the real number line such that irrational numbers that are not rational, are, let's say, red, and rational numbers are blue, then there would be no blue. You would only see red. Like we're really talking like, the difference between uncountable and countable. We're really talking about like individual atoms versus like a big object in space that you can look at. That's how granular something countable is compared to the sheer size of something that's uncountable. It is a fundamentally bigger thing. Both of these arguments were measure theory arguments. To connect this back to kind of computability, if you were to generate an infinite sequence of binary numbers, an infinite binary sequence, via coin flips, then the language that is associated with that infinite binary sequence. Remember, we can think about infinite binary sequences as languages. So I can construct a language by flipping a coin infinitely. If I flipped a coin infinitely many times to generate a binary sequence, then the probability that the resulting decision problem is computable is 0. The probability that you land in a in R when you generate just a completely random infinite binary sequence is 0. It's kind of the same as the dartboard argument. So yeah, I mean, that's just to give you a sense of how much bigger it is to be uncountable versus countable. These all require a bit of measure theory to really flesh out in your understanding, but that's the idea. That's how much bigger uncountable sets are than countable sets.